I'm going to start. Thanks a lot for coming to my presentation. The title is Characterizations of birefringence with elliptic eigenmodes in a wave plate composed of two quark wave plates. My name is Jhon Stivenson Pabón Niño. I'm a physicist, and currently I'm making my master's degree in applied mathematics in the Universidad of Santander in Colombia. So thanks a lot for the opportunity. This is the content of my presentation. I have 5 parts. First of all, I'm going to introduce the topic, that is polarized life. The second part is birefringent materials, that are a kind of materials that we could use for change the polarized state. And the third part is the system that I study, that is a biplate of two quark wave plates. First is the results, experimental and theoretical results, and finally the conclusions. First of all, I'm going to introduce the topic, that is in general the polarized life, that in general is the characterization of a life that describe the shape of the electric field is describing during the propagation. So in general, we say now ellipses of the this is the most general form of the polarized life, that in general this is the form that we have, like a particular case, the linear polarized states or circular polarized states. The about the mathematical for describe the polarized life would change several algebra. First of all, would change the Jones vector, the R2 vectors. However, we can describe these ellipses in equivalence angles of azimuth and ellipticity, that we are going to use this representation of Stokes vectors. So this has several properties, and we're going to work with the Poincare sphere, that when we use these Stokes vectors and we normalize them, we obtain a simple representations of the Poincare sphere, that every point on the surface of the Poincare sphere is a polarized life with azimuth or an ellipticity fully describe it. So this is very important for our work, because we are going to use this Poincare sphere representation for the space of polarized life. So all the chains in the state of life, we could obtain a curve on Poincare sphere. So about the polarized life, we obtain, or we are going to describe how we can change these states of life. So one of the most used for are from birefringent materials. We're going to use the geometric algebra approach of quaternion algebra, that in general a birefringent material or any transformation in general, it could work from classical or quantum theory of polarized life. Every change in the state of polarized life, it could be described like a rotation on Poincare sphere. So in general, the most powerful tool are geometric algebra approach of Pauli vectors and quaternion algebra. So in that way, every change of polarized life could be described in that form under a rotation. In that way, the E sub q is the axis of the rotation, that in the case of birefringent materials are the eigenmodes. And this angle is the birefringence. This angle of rotation is at the same way the birefringence of the material, the phase retardations. So this is a very important, more general mathematical tool that matrix algebra do it too. Only changing this vector, we can obtain several eigenmodes, circular, linear, or in general elliptical eigenmodes, only when we vary this axis of rotations. So it's a more general framework for work in polarized life. So this is the representation that we're going to work. This is the birefringent materials in general, are anisotropic materials that introduce phase retardations through the eigenstates of the birefringent material. In general, they could be linear, elliptical, or circular eigenmodes. First of all, the most used for is linear birefringent materials that is very useful in wave plates, that commercial wave plates, half wave plates, quarter wave plates. There are linear birefringent materials. Due to they have linear eigenmodes. When we inside linear state, we could obtain in a specific rotation of the wave plates the same output state. So when we rotate this material, we could obtain the modulation polarized life that in general under the Poincare sphere, on the Poincare sphere, we could obtain a curve. This is the it have been characterizations in under the law of geometrical law of birefringent materials with the geometric form that all the states that could emerge when we rotate them on the Poincare sphere would obtain this kind of curves, for example, that they could be described like the curve of the intersection curve formed by the Poincare sphere and a cone, and the angle of the cone is the phase birefringence of the materials. This is a geometric law that we are going to work, and we're going to make a generalization on elliptical eigenstates in general in any birefringent material. So in that way, these are the linear eigenmodes used for wave plates, but in general, the birefringent material or the most complex media obtain elliptical eigenmodes like photorefracted crystal, biological media like cornea, the optic nerve, the tissues in general, and another in optical system like optical fiber, liquid crystal in metamaterials, and in general decomposed wet plates. That this is the setup that I use. That is the combinations of several linear wave plates. So when we combine them and when we rotate one to each other, yes, we obtain a new eigenmodes, a new retardation. This is the main idea that we are going to work. So in general, when we obtain a simple combination of two, this biplate, and we inside a linear polarized state, in general, we obtain the output is another one to linear state. In general, it's elliptic. In that way, we obtain that it still exists elliptical agent state that is the agent mode of the composed system. This is the mathematical that we're going to resolve in the way. So we obtain two quarter wave plates with linear eigenstates, and this compose or this product in quaternion algebra approach we obtain a single simple elliptic and eigenmodes with retardation and eigenmodes analytically described. So this is the most important equation that that we resolve. That this is the product of the both linear quarter wave plates with theta tilde is the angle between both. In physical space is the rotation in the fast axis between the both. So this is the product of the two quarter wave plates. That this term in E3 implies that in general is birefringent with elliptical eigenstates. So this is true due to the groove theory under the rotations. So in that way, we could resolve this equality to obtain the analytical form of this system. On the other hand, we use the Jhon's theorem that implies that any composed wave plates or any birefringent with elliptical eigenstate could be decomposed like a composition of optical activity and linear birefringence. So in that way, we use this double equality to describe or to make a full characterization of this composed system. So this is the experimental setup that we use for that. We use a laser, a coherent laser. We use a collimator lens to obtain a wave plate. We use a linear input state with a crystal, and we inside this state across the composed waveplanes. And we measure the polarization states using a polarimeter. So our idea, our hypothesis is like all the states that we can generate with this composed waveplate during, we can change the angle between them, the theta tilde, and the rotation of both at the same time. We could obtain a specific curve on Poincare sphere. So our idea, our hypothesis is the same like linear state with a cone plus a rotation due the optical activity. In that way, we could obtain a general framework to obtain the characterization of all birefringence material with any eigenmodes. So in we obtain a result, we obtain a characterization. The first result that we obtain is an analytically characterization for any birefringence with elliptical eigenmodes on Poincare sphere. That in that way we obtain that the input state describes the geometric form of the vector of the law, the count, and we obtain all the analytically formulation for any birefringence with elliptical eigenmodes. So the law that we generalize is the all the emergent states resulting for propagation of a light through the birefringent media is characterization with the intersection under the Poincare sphere and a rotated cone. The angle of the cone is due to the linear birefringence and the rotation is due to the optical activity. This model is more general due to is a geometrical form that obtain the linear birefringence like a particular case, and on the other hand, the optical activity is a particular case too. And about the experimental results, we use the biplate and we inside input polarized light, and we use first of all theta tilde in 0 and v half. That's the main idea is in where 0 there are the two quark waveplates in parallel 4, and in the other hand is when there are orthogonal 4. So the first way that we are in parallel 4 we obtain the same behavior like a half waveplate. In other hand, when we are both or in orthogonal 4, the retardation is 0. So the main idea in that way is that when we can shade this angle, we can obtain new feature of our composed waveplates. New feature, new retardation, and new eigenmodes. So this is one of the most important results that we obtain, that we can obtain only two quark waveplates, and when we rotate one to each other, and due to this angle, we can obtain tunable birefringence material. So this is a mechanical form to obtain variable retarders. On the other hand, we measure the retardations due to the angle of the cone and the optical activity, the rotations due to the input to the vertex of the cone. This is the analytical form of the rotation, linear birefringence, and the axis. This is a very simple analytical form to describe this complete system. So this is one of the most important results that we have. On the other hand, we obtain the tunable eigenmodes. In that way, is the same. We only change the angle between the both quark waveplates, and we obtain a retardation, elliptical retardation, and elliptical eigenmodes. This is, for example, the experimental results. This is these results. We can see that this is all that we propose in the work, because this is the input states that is generated in the core of the waveplate. So this is the input state, and this is the output. So we in that way we obtain the elliptical eigenmodes. This is the ellipticity of the form that only depends of the angle between them. And on the other hand, this is the overall retardation of the system. And this is the law that we propose, that this is the vertex of the cone, and we can see that we completely make a characterization geometrically, analytically, and experimental of the birefringence with elliptical eigenmodes and a specific system of two quarter-wave plates. And in conclusion of my work is we obtain a compressive characterization of the biplate of two quarter-wave plates. We establish the birefringent media with elliptical eigenmodes, and this formulation obtaining very simple, very simplicity due to the geometric algebra approach is direct. Due to it depends only of the retardation and eigenmodes. Is the most important and used mathematical behavior of this algebra. On other hand, to the matrix algebra like Jones or Stolberto, that it could be very difficult to obtain the same result that we obtain here. Furthermore, we obtain a geometrical log on Poincare sphere that could be worked in general for any birefringence materials and in a very simple and intuitive form that is a cone and a Poincare sphere. This work and this result has been published very recently in Journal Society American A under the title To Enable Birefringence and Elliptical Polarization Eigenmodes in a Biplate of two quarter-wave plates. So thanks a lot for coming, and I'm very thankful to respond any question that you have. Thanks a lot.